Welcome back, Chemistry 30. This is the section 20.2 on redox, and here we're looking at balancing redox equations. So we looked at how we apply oxidation numbers, and now we'll take a look at how we can use that to in fact balance an equation. So you already know that chemical equations are written to represent chemical reactions by showing what substances react, what products are formed. You also know that chemical equations must be balanced to show the correct quantities of reactants and products. Equations for oxidation reduction reactions are no different. In this section, you'll look at a specific method to balance redox equations. So the oxidation number method, many equations for redox reactions are easy to balance. For example, try to balance this one. So we could do this one just regularly. So of course we have 1K, 1K, 1Cl, 1Cl, 3 O's, 2 O's. So of course the lowest common multiple of 3 and 2 is 6. So I'll need to have 6 oxygens here. That means putting a 2 in front of there, a 3 in front of here, so that gives me my correct number of oxygens, and then balancing out the Ks and the Cls. So equations for other redox reactions are not easy to balance by conventional means that we have learned up to this point. So for example, if we look at this, it's quite difficult, and the primary reason is because we have oxygens in many different compounds here. Oxygen here, oxygen here, oxygen here, oxygen here. When you have oxygen occurring in many different compounds, it's very difficult to balance by conventional means. So that's what I mentioned here. Note that oxygen appears in only one reactant, but it's in all 3 products. Redox equations such as this, in which the same element appears in several reactants and products, could be hard to balance by the conventional method. For this reason, you learn a different balancing technique for redox equations that is based on the fact that the number of electrons transferred from atoms must equal the number of electrons accepted by other atoms. So what one thing is gaining, the other thing is losing. So put a star beside that. That is the key thing there. There must be an equal transfer of electrons. If something is losing, something is gaining. So as you know, when an atom loses electrons, its oxidation number increases. So losing electrons, oxidation, you get more positive. So that's what we mean by increases, gets more positive. When an atom gains electrons, reduction, its oxidation number decreases because we're getting more negative. So that is where the word decreases come from. So if we're getting more positive, oxidation number is increasing, we're actually losing electrons. If the number decreases, it's becoming more negative, we're actually adding more electrons in there. So therefore, the total increase in oxidation must equal the total decrease in oxidation of the atoms involved in the reaction. This balancing technique is called the oxidation number method. It's based on this very principle. So what you may want to do is highlight and star this section here. Later on I'll ask a question which you put these steps in order, so make sure you have this. So steps for balancing redox equations by the oxidation number method. So assign oxidation numbers to all of the atoms in the equation. Identify the atoms that are oxidized and the atoms that are reduced. Determine the change in oxidation number for the atoms that are oxidized and for the atoms that are reduced. Number 4, make the change in oxidation numbers equal in magnitude by adjusting the coefficients in the equation. And lastly, if necessary, then use the conventional method that we're used to balance the remainder of the equation. Okay? So we'll look at an example doing that, and then I have a few questions that we'll do right here. I have them worked through, so we'll go through that. So it says here, balance the redox equation shown here for the reaction that produces copper nitrate. So there we have it right there. So the first step there, of course, as mentioned, I assign oxidation numbers to each item. So of course, copper by itself, so it's 0. HNO3, oxygen is the most electronegative one, so it is -2. And I didn't write underneath here what the totals are, but you may wish to do that. So of course, -2 times 3 is -6. This whole thing's going to have to be 0. Hydrogen, in this case, is +1, so that means nitrogen is going to be +5, and then individually there are numbers. Over here, oxygen is -2. I actually have 6 oxygens, so -2 times 6 is -12. It's going to have to equal 0. And the copper that I'm using here, since I need 2 nitrates to balance 1 copper, it's copper 2, so copper is +2. So remember here, folks, I had -12 plus 2 And so negative 12 plus 2, so that's going to leave me with 10. Plus 10 I'm going to need for nitrogen, but of course I have 2 nitrogens, so 10 divided by 2, 5. Yeah, so you may will find it easier to write those totals underneath here like I did previously. Oxygen's more electronegative than nitrogen, so negative 2. Negative 2 times 2 is negative 4, so this has to be plus 4. And then water like that. So you can see the things that are changing here. Hydrogen does not change. Copper, it's going from 0 to plus 2. So copper is undergoing oxidation. Lose electrons, oxidation is getting more positive. Nitrogen went from positive 5 to positive 4. It went down by 1. It's getting more negative, so it was reduced. So the next step there is to write down that change that's happening. So before we would talk about oxidation or reduction, now we're just going to look at the change that's happening. So copper, to go from 0 to plus 2, we're adding 2. Nitrogen, to go from plus 5 to plus 4, we're subtracting 1. Okay? So far, we've done these steps. We've done this. We've identified what's oxidized and what's reduced. We determined the change in oxidation numbers. Now we want to make the change equal by adjusting coefficients. So before we can do that, we have to make this change equal. Plus 2 minus 1. So of course 2 and 1 go into 2. So you can see here, if I double this, I'll have the right change. So doubling that means I'm going to have not 1 nitrogen, but 2. So doubling that, I'm going to have to put a 2 there. 2 ends. So my change in oxidation numbers will be the same, gaining 2 here, losing 2 here, so that's what we need to do. And then lastly, we just need to figure out, okay, what else needs to be balanced here. So then, just like rule number 5, you've used conventional means to balance the remainder of the equation. So if I look at the next part here, I have that 2 and that 2. And of course here, what am I missing? The coefficient, okay, so I have 1 copper, 2 ends, 6 O's, 6 O's, but I have extra over here as well. So the coefficient in HNO3 must be increased from 2 to 4 to balance the 4 nitrogen atoms. And I missed that actually. There's 2 ends here, 2 ends here. So I need a total of 4 ends there, so to make the ends work out, I have to bump that up to 4, and then I think that works out. All right? And also with that, that's also going to change. If I have 4 ends, that's going to be 4 H's, so I need to have 4 H's here by putting a 2 in front. So you can see, a little tricky. The key thing is figure out the oxidation reduction part, and then go from there. All right, so on a piece of loose leaf, we're going to run through these practice problems. Then part 2 of the video, we're going to look at balancing net ionic equations, and we'll have another set of 3 questions to do. So if you grab a piece of loose leaf, you could likely fit all of this on there when we in fact do that. So if you look here, use the oxidation number to balance these redox equations. So here they are right here, gang. So if we look here on this page, here's that first equation. What I'll maybe get you, we're almost at 10 minutes in this video, so I'll maybe get you to first of all write down the oxidation numbers that we have here, and then figure out the change, and then maybe see if you can balance it. See if you can balance the oxidation reduction part, and then the lastly part, you'll use conventional methods to finish it off. Okay, we'll see you again.